Okay, welcome to another one of my video log recording sessions where I talk about genetic algorithms and basic stuff, and hopefully onto more advanced stuff. I think I'm these days, for the past few days and for the past few previous videos, I am on the edge of the basic stuff and what I can probably call the advanced stuff. So right now I think I am in that intermediate zone. The date is 2025, April 3rd, and it's 2:56 in the morning, AM. And today I'll try to cover 7 notebooks. This, and this. So, and this one is just from one of the previous videos. I just put it up here just to show the comparison, the difference between what I did. Yeah. So what if anyone were to watch the past videos, you'll remember that I would have to redo the work I did, and so I did. I kind of revised these 7 notebook files. Each of them took about 100 minutes to run, so that's about 700 minutes, which is more than 10 hours. So that's what I did today. So the first one is, let me get that paint, and it's the same in this. So what I did in these notebooks is that I would generate a number of items. I would generate a number of items from 1 to n, and I would generate the utility values, val 1 to n, and constraint values 1 to n. And I would fix it. I would have these values fixed, and then oh yeah, I forgot to mention, I would choose a distribution where I could sample these values, from which I could sample these values. For example, the first notebook is from the normal distribution. Normal, and then it's log normal, and then it's uniform, and then it's exponential, and then it's von Mises, and then it's Pareto, and then it's Weibull. So, hey, anyway, let me type that again. Normal, log normal, uniform. Yeah, so that's why I have 7 files. So I would sample these 2 sets of values from one of these distributions, or one of these types of distributions, with all the parameters, but the parameters would be the same. But these 2 are still from the same distribution, just sampled separately. So I haven't done that bit where I sample, for example, utility value from normal and constraint values from exponential. I haven't done that yet. I plan to do it in the future, and for that, if I were to calculate it, it takes about 100 minutes, and there are 7 of them, so I need to pick 2. It could either be normal and then uniform, or uniform or normal. So 7 times 6, so that's 42, and times 100. Yep, so that's about 70 hours. 70 hours. But that's not what I'm doing today. Or that's not what I did today and for the last week. So, 7 notebooks. Values fixed. From one of these, sampled and fixed from one of these distributions, and do 5 evolutions for 500 generations. So 5 iterations for 500 generations per max constraint percentage. Same percentage. And so by having this value, I can multiply this value by the total sum of constraints and then use that as the threshold, the maximum constraint. And anything that goes above it, any entity that goes above it, will be struck out. So that's what I did. Let me just type that again. Normal, log normal, uniform, exponential, what was it? Von Mises, Pareto, that's 6, and last label. Yeah, so that's what I did. The first notebook is using the normal distribution for the utility values and the constraint values, and I would do what I just described 3 times. First is when n is 10, n being 10. The second will be 40, and the third will be 100. So that's 10 items or 10 genes, 40 items or 40 genes, and 100 items or 100 genes. And I run that. This video is going to be quite long. And when I run that, this is the distribution of the entities. Well, a snapshot of the final iteration of the evolution. And the maximum ever. Well, let's get things clear for now. I mean, so for 10 items, I generated 10 items, and the maximum and the total sum of utility values is around 1000, because they're all the values sampled from the normal distribution are all centered around 100. So naturally, if you have 10 items, the total sum will be around 1000. So that's the sum, 998. And the same goes for the constraint values as well, and the total sum of constraints is 1000. So when I have 10 items, and then when I go through all the maximum constraint percentage, which goes from 5%, all the way to 100%. Yeah, 100%. So anyway, and this is the final state. But again, for this, the maximum constraint percentage is 100%. This histogram is just to show that the distribution of entities follow somewhat of a normal distribution, like the theorem, yeah, where everything just follows normal if you just add them up or something. So the maximum value ever was 900, and the total sum of utility values was 998. That's okay. I mean, it looks okay, doesn't it? So, by the way, this is the first time I'm actually going over these results, so that's why I'm just stuttering and rambling and mumbling, so my apologies. So anyway, maximum ever was 900, and we'll see soon where that was. And the average peak, we will calculate the average peak. So this is what's different from one of the last videos. I would calculate the average peaks, and I would calculate the average plateau using the plateau function that I made, which is right here. Getting the plateau by calculating the average of averages, or the average of moving averages rather. And when I do that, this is the plot. This is the plot for the average dip size, and this is the plot for the average dip percentage. You'll see that it goes up, and this is what I overlooked last time. It ended here, and I just didn't think about plotting the overall performance, or overall total sum utility values of entities, or the or the average of top 10%, average of the top 10% entities. So anyway, the maximum dip percentage was 9%, and here we go. Let's plot it. Let's plot everything. So plotting the heads, or the top entities, at 5% when maximum constraint percentage was at 5%, you'll see that there's basically nothing, which is, obvious, because when the maximum constraint percentage is so low with so few items, the entities just don't change much. This is when it is at 10%, 15%, 20%, 25%, 30%, 35%, and so on. But before I go on, I'll just have to point out that the black line is the maximum ever, and the red line is the total sum of utility values. So right now we're not seeing that, because I forgot to put in the red line. This code was this line was added after, but I didn't run it because it would give me the same results and it would take me some more time. So just keep that in mind. So the black dashed dotted line is the maximum ever, and you'll see that as the maximum constraint percentage goes up, the plots actually start going higher and closer and closer to the black line. And at 75, 80, 85, 90, 95, 100. So one thing that I should just mention right now, and this will come up more as I as I switch the notebooks, and it is the fact that when there are so few items or so few genes that we're dealing with, we actually reach the maximum ever as the maximum constraint percentage goes up. However, when we have more than 30 or 40 items, that's not the case, and we'll see why, or rather I'll talk about why I think that is the case. So here are the plots for the top 10%. Again, nothing there, because, well, at 5% there isn't a lot of room for the entities to grow, and at 10% we start getting some progress, 15% slightly more progress, and the average plateau being 100, average plateau being 101, average plateau being 200, 201, 300. At 35% it's still at 301, at 400 it's 401, at 45, 401, 50, 500, 55, 501, 60, 599, so almost 60. At 65%, it is at 600, 70%, 674, 75%, 695, 80%, 724, 85, 735, 90, 750, 95, 760, 100, 759. So, as you can see, the average dip percentage goes all the way up to 8.76, or rather 9.11%, so around 9%, but that's because they peaked. However, one thing to note is that we're still dealing with 10 items. One thing to note here is maybe here, or maybe I should mention it in the next phase. Yeah. Yeah, I think that goes for this one. So that's how it goes. Let's see what happens when we have 40 items. So we generate the 40 items. The total utility sum is 4004, and about the same for the total sum of constraints. And then we set the hyperparameters, population size being 1000. Oh, by the way, the hyperparameters are almost all the time the same. And we run the whole thing, and this one takes about 1600 seconds. So that's about slightly less than, maybe it's 28 minutes. I'd give, more or so, give or take. And here is the entity distribution at maximum constraint percentage 100. It's this last slice, or the snapshot. The maximum ever was 3,500. Again, the total sum is 4,000. So we still did not reach the 4,000 mark. And we calculate the average peak, we calculate the average plateaus, average peaks and average plateaus, and we plot it out. So here, now that we're dealing with more than 10 items, in this case 40 items, this happens. The average dip percentage, or the average dip size, just plummets after some point, after some maximum constraint percentage value. And in my last videos, I mentioned that this is because of the fact that when the maximum constraint percentage value is so high, and therefore the maximum constraint is so high, no entity actually gets struck out, and there's little to no procreation amongst the top 10% entities, for example, and therefore there is little to no innovation. But anyway, the maximum dip percentage was 9%, or 9.8%. And here are the generation to summed utility plots. First up, heads. So average dip, but anyway, at 5%, this is what happens. Nowhere near the maximum ever. At 10%, same. 15%, same. 20%, same. 25%, boring and same. I need to sneeze. Sorry, I had to sneeze. At 30%, same and boring. At 35%, same and boring. 40%, same and boring. 45%, same and boring. 50%, slightly more progress, but still the same. 55%, I don't know where that one comes from, but again, same. at 60%, about the same. Now at 65%, same. 70%, same. 75%. No, well, 70. Starting from 70%, it gets interesting. 75%, same. Interesting, but same more so. But now there's more oscillation. 80%, very interesting. A lot more oscillations. But we're still trying to reach the maximum ever. At 85%, oh, now we're getting there. At 90%, we finally have some values reaching the maximum ever. And funnily enough, at 95%, we don't reach the maximum ever. At 100%, we do have one instance where we reach the maximum ever. Now, let's have a look at the plots for the top 10%. 5%, almost no progress. 10%, same. 15%, same. 20%, same. 25%, same. 30%, same. 35%, same. But we do now see that slight curve there. 45%, same. 50%, same. 55%. Now we see the peaks and plateaus starting to separate, and we can see those two lines. Plateau in yellow, plateau in blue, and the peak level in yellow. At 60%, same. 65%, same. 70%. Now we see some peaks. Yep, and the average dip percentage was 3.4%, whereas at 65% it was 1.75. At 75%, the average dip percentage is at 7%, and the average plateau is 25.32. At 80%, the average dip percentage is at 9.88. Average plateau is at 25.45. At 85%, we have the average dip percentage at 7.5, and the average plateau to 25.35. So this is one thing that's sort of weird, is that when the maximum constraint percentage was at 80%, the average plateau was 25.45, but now that the maximum constraint percentage is higher, the average plateau is actually 10 lower. And this could be due to the fact that again, with this value, maximum constraint percentage, and therefore maximum constraint being higher, there are actually fewer entities being struck out, and therefore fewer new entities being created through procreation amongst the top entities. And the same phenomenon happens when the maximum constraint percentage is at 90%, and the dip percentage got lower, and at 95, the plateau went down compared to 25.45. Now it's 25.28, and at 100% it's 25.30, the plateau level. However, the dip percentage is 3.25, but so a small dip exists here. However, we're nowhere close to the maximum ever. I mean, if we were to take away 10% from this, or maybe 20%, it might be, it might be nice to find a way to raise this plateau level all the way up to maybe 3,000 or slightly below 3,000. So that was 40 items. Now let's have a look at 100 items. Generate the values, total sum of utility, almost 10,000, total sum of constraints, almost 1,000, almost 10,000. So 10,000 here and 10,000 there. And when we run everything, this takes about an hour, so around 3,600 seconds. So this is the distribution, and maximum error was 7,502. And we calculate the average peaks, the average plateaus, and we look at the dip plots, average dip percentage plot. Again, same phenomena here happening. So this is purely because because there's little to no procreation. So and we plot it. Here are the heads, and we see the black line for the maximum ever. Same thing, very boring stuff until maybe at 65% or 55%. Yep, now we're getting some values, and then now a lot more oscillations there at 70%, even more oscillations, 75%, even more, 80%. Yeah, when do we reach the maximum ever? Maybe at 95. Here we go. We did reach the maximum ever, but we'll see what happened at maximum constraint percentage 95 for the top 10%. So let's just jump right to it, and maybe start from the bottom. This is what happened at 95. So we were very lucky that we did get the maximum ever value from here. We got really lucky. However, there were no peaks here. And I say that because the maximum ever was 7,500-ish, and we were lucky there at 95. But when we did have peaks, for example here, the average peaks were 6,333, so 6333. We got to 95, and then the average peaks were less than 6,000. So this means that except that one top entity that hit the maximum ever, all the rest were just not doing their jobs in terms of evolving. So this phenomenon always happens when the maximum constraint percentage is so high, and given the way I'm evolving the entities, when the maximum constraint percentage is so high, the selector doesn't work, and therefore there's little to no procreation. So that's what happens when we use the normal distribution for the utility values and the constraint values. Let's move on to the log normal, and same thing, just sampling except that the two sets of values are being sampled from the log normal distribution. And when we have when we look at the distribution, entity distribution, this is what it looks like. Now let's have a look at the average dip plot. Very similar when dealing with only 10 items. Same for the average dip percentage plot, but maybe something more different here for the heads. Same thing, Now the red lines starting from here mean the total sum of utility values. Right? Yeah. Total sum of utility values. So let's see when the head actually reaches the maximum ever. Oh, by the way, the yellow lines are always the peak levels, and the blue lines are always the plateau levels. So when we had the maximum constraint percentage value at 95 and at 100, we did quite consistently keep getting the maximum ever values repeatedly, but this is because we only have 10 items, 10 genes, so it's very easy to just converge to that level. And for the top 10%, again showing progress as the maximum constraint percentage goes up. 45, 50. Now we start seeing the separation of these yellow and blue lines. At 85%, we do start getting peaks. At 90%, we did have some peaks, and therefore some plateaus, being 6% and maybe 3.8% for that. At 95%, the average dip percentage is at 8.5. At 100%, the average dip percentage is at 9.45. So again, when there are only a handful of items, peaks will happen when the maximum constraint percentage is near 100%. Hence this plot. Now let's have a look at 40 items, setting the utility values, and this is the distribution, and total sum of utility values is 1042. Total sum of constraint values is 1434. And we do the evolution. Here's the distribution. Here's the the dip plots, dip plot and the dip percentage plot. Again, we start getting that because now we have more items, more genes, and then higher maximum constraint value. Again, I'm going to repeat myself, but higher maximum constraint percentage value means that little to no entities are being struck out, and therefore little to no procreation happens. Maximum average dip percentage is at 15%, and here are the plots. Maximum ever, what was the maximum ever? 1024. And the red one is the total sum of utility values. So let's see when we hit that maximum ever. It is when we have the maximum constraint percentage at, in this case, 85. Keep that in mind. 85 and 90. Oh, these look very interesting, right? So when we look at the plots for the top 10%, let's pay more attention to 85 and 90. Yep. So let's have a look. 85 and 90, we still don't see the plateaus and the peak levels separate. I wonder why I'm getting that. It's just now we start getting the average the percentage above 3%. .25% average the percentage, because now we do have some peaks. But again, very interesting thing to note here is that when the maximum constraint percentage is at 65, the average plateau is 792. But when it's at 70, although we did get some peaks, the average plateau is at 757. This is lower. And also, not to mention, when it's at 65, the average peak is also at 824. However, when the maximum constraint percentage is at 70, the average peak is at 808. This is still lower. So it seems that because more entities got struck out, more innovation happened, more changes, more mutation, more procreation and mutation led to more innovation and raised both of these values. Same story for when maximum constraint percentage is at 75. At 80, at 80%, it's worse, because now the average peak is at 827, but the average plateau is even lower than that. And I said 85 and 90. Let's have a look at what happened. Average peak is 851, but the average plateau is at 728. So still lower than when this value was at 60%. And max constraint percentage at 90%, 857, so higher, but the average plateau is still lower. 95%, everything is just lower. 100% lower. So now, let's have a look at 100 items. So, generate the 100 items, and the total sum of utility is 3541. Total sum of constraints is 4268. And voila. Entity distribution, still a normal distribution. Again, yeah, the central limit theorem. Maximum error is 3383. And the total sum is what again? Total sum is 3541. Maximum error is 3383. So kind of close. Average peak list, average peaks and average plateaus. Yep. Plots again, same, and trailing off. Well, the dip percentage just falling down as usual. Let's have a look at when we get the maximum ever, the black line. When we reach the black line. Here. No. Here. At 50% we do. 55% we do. 60% we don't. 65% we don't. 70% we don't. 75 we don't. 85, 80 we don't. 85 no. 90 no. 95 no. 100 no. So that's just really odd, because when we had the maximum constraint percentage at 55. And the total sum yeah, like seriously. Okay, but what was I looking at here? So higher maximum constraint percentage, less innovation, as usual, as we've seen multiple times by now. For the top 10%. Yeah, about the same results. This, for example, this one is quite lucky. Out of the 5 iterations, only one iteration we had, in only one iteration we had a peak. And also, as the maximum constraint percentage goes up, the average plateau level gets lower as it goes above 80%. Interesting. Now, for the uniform distribution, when using the uniform distribution, same distribution there, central limit theorem, average dip percentage, same when we are dealing with 10 items. What was the maximum ever? 3.92. So let's see when we hit that. Towards the end, of course. 85, not so. At 90 we do. At 95 we definitely do. At 100 we do. Plots for the top 10%. Now we get some oscillations and peaks and plateaus. Now the average plateau level going down. Yeah, when the average plateau level still went down. Probably because there's, again, less innovation. I wonder why, I should look into why I have this pattern when I only have 10 items. I should definitely look into that. So 40 items, generate the 40 items, calculate the total sum of utility values, total sum of constraint values, and run the evolution. Yeah. What was the maximum ever value? 19.38. Average dip percentage plot, as usual. maybe I should. When do we hit the maximum error? At 80 we do. No, at 85. Now, we'll have a look at the top 10% when the percentage is at 85. Okay, cool. Let's jump straight to 85%. Okay. Okay. 14. But the average plateau is at 12.79, and the average plateau level has 12.79 has been going down ever since. Yeah, the average plateau was at its highest when the maximum constraint percentage was at 50. And then it just kept going down. Yeah, so these are quite, well, I don't know. 85. Yeah, these four peaks were quite lucky. No, we got lucky. Okay, 100 items. Utility values, total sum is 53.26. Total sum of constraint values is 48.52. And assessment, yep, distribution, central limit theorem again. Maximum error is 45. And dip percentage plot, as usual. Heads. Yep. Total is red. Total sum of utility values is red. Maximum error is black. Let's see when we hit it. Again, most probably towards the end, I think. Or not. 70. At 75 we hit it. At 80 we don't hit it. At 85 we don't hit it. At 90 we don't. 95 we don't. 100 we definitely don't. So we jump straight to 75. Yep, that's why we hit the maximum error value there. Again, the average plateau level is probably going down. Yeah, it was 35 here, it was 38 here at 50%, 38 here at 45%, but when we did have the maximum error value at, what was it, 80? Yeah, no, 75, the average plateau is at 31. So not that much of an innovation going on there. Yeah. And let's have a look at the exponential distribution. 10 items, average percentage plot, usual, heads. When do we hit the maximum value? I don't know, max ever was 4.08. When do we hit that? Again, probably towards the end. At 100% we hit it. So let's have a look at when it is at 100%. Peaks. But this, again, we're dealing with 10 items, so this is why it's happening at max constraint percentage 100%. And when we have 40 items, total is 22 for the total utility value. Total for the constraint values is 23. Remember, we're using the exponential distribution. central limit theorem again. Maximum error was 21 out of 22, so that's pretty close. Average percentage plot, average dip percentage plot, as usual. So when do we hit the max ever? That is 21. At around, no, at 85% we hit it. So we'll go straight to 85. Yep, that's why we had the, well, I don't know if that's actually why, but we did have peaks, and the dip percentage were the average dip percentage was 16%. But then again, the average plateau level was probably going down. See, it was at 50.97, and then it was 15.14, and then it's 14.8, and then it's 14.72, 14.72, 14.57, and at 100%, 14.56. So again, no innovation there. Which means that if I were to introduce procreation there, if there were a procreation there, this whole plot, this whole level would just be higher. The plateau levels and the peak levels would be higher. So 100 items, setting the utility values. Total sum of utility values is 83. Total sum of constraint values is 80. And when we have that, the maximum error, when we have 100 items, the maximum error was 75. So 5 units away from the total sum of utility values. No, 8 units away. 8 away. Average peaks, average plateaus. Let's have a look at the heads. When do we hit the maximum error? Probably again towards the end, right? No, almost at 55% too. At 60% we do. At 65 we don't. At 70 we don't. 75 we don't. 80 we do. We have to look at that one. 55 and 80 we have to look at that. 85 no we don't. 95 no. 100 no. So it was at, what was it? 55 and 85? 55, 60, 55, 60 and 80. So going straight there, 55, 60 and 80. 55, 60, and 80. Okay. Cool. But the plateau levels are all going down, aren't they? Yep, 57, 62, 66, 67, 66, 64. And when the maximum constraint percentage is at 85, 50, 50, 50, 50. Okay. Von Mises distribution, 10 items. Let's just make this quick. That's what it looks like. Total sum is 31. Total sum of constraint values is 24. Distribution is looks like this. Maximum ever was 31. 31 out of 31. Well, that's good, I think. 3184. 3184. 3175. So that's pretty close. Then again, we only have 10 items. So usual Hence, when do we get it? Probably towards the end again. Probably at 100%. At 80 we almost did. At 85, 90, 95, 100. Yeah, so I guessed right. Let's have a look at the top 10%. It's going to peak and plateau at 100% probably. At 80 we do that. 85 we do that. At 90 we do. At 95 we do. At 100% we do. But again, the plateau level kind of went down. It went up and then came down. Yeah. 40 items. As usual, the average dip percentage plot. And the maximum average dip percentage was 17.4%. The total sum of utility is 133. And the maximum ever was 131, so that's 131 out of 133. Heads. When do we reach that? When the maximum constraint percentage was at 80, we have that value. 85 we have that value. 90 we don't. 95 we don't. 100% we don't. So 80 and 85. 80 and 85. But I still see the average plateau levels just going down, because it was at 94 and the average peak was 100. Average peak is at 102 and it's 90. Average peak is 104 and it's still average plateau is at 90. The average plateau was 107 at max constraint percentage 55 and 50. Yeah. 100 items. Utility values, total sum 317. Constraint values, total sum 301. So it's 317 is the total sum. And here's the central limit theorem. 317. 303 out of 317. Okay. Average dip percentage plot, as usual. When do we hit that 303 out of 317? The red line being 317 and the black line being 303. But when do we have it? At 50% we almost did. Maybe we did or not. At 55 we did. At 60 we didn't. 65 we didn't. 70 we didn't. 75 we didn't. 80 we almost did. So this is unusual, so we have to look at 80. 90, nope. 95, no. 100, no. So 85, 55. 50, 55 and 85. We look at that, go straight to it. 50, there we go. Okay, 55. Average plateau level going down. 85. 80. There we go. But then again, the average plateau level is still going down. It was at 243 and it went down to 194. That is a hell lot lower. That's really, really, really low. Got a lot lower. Yeah. So that was von Mises distribution. Pareto. This is a long video. It's already 59 minutes. So generate 10 items, and then that, and this. Let's just have a look at the average percentage plot. Usual, heads. When do we reach it? Probably at 100%. At 90 we almost did. 95 we do. At 100% we do. Now, let's go to 80, 80, 85, 90, 95, 100. So 10 items, usual. At 40 items, essential limit theorem, maximum ever, 55. When do we reach average dip percentage plot? Usual, as expected. When do we reach? When do we hit the black line? When? 80% we don't. 85 we don't. No, we do. 85 we do. 90, 95 no, 100 no. So top 10% we go to 80 and 85, and let's have a look at that. 80, 85. But plateau levels still going down. It was at 39 once, 40, but in the end it goes down to 38. Ouch. 100 items. Entity distribution. Maximum ever being 1 to 1 out of 152. Average dip percentage plot as usual. Heads. When do we hit that 1 to 1? %, 75, 80, 85, 90, 95, 100. No, I missed that. When do we get it? Oh, at 70 we do. So at 70 we go to 70. Max constraint percentage 70. The average dip percentage 9.48. But then the average plateau is still decreasing, isn't it? Yep. The highest it was 96. And then now at 70 and 80, 75, it's at 92. $92, $92, $92, $92. Huh. And Vable, I still have to start Google how you read that. Utility values, constraint values, average dip percentage plot, yeah, usual, heads. Yep, usual behavior when you only have 10 items. For the top 10%. Yep, towards the end. Peaks and plateaus towards the end. Okay, 40 items. Average dip percentage plot, usual. Heads, when do we reach it? $85 we do. 90 we don't. 95 we don't. 100 we don't. So we go to 85. No, 80? 85, right? 85. We go to 85. 85. The plateau levels are going down. There we go. But then again, the plateau levels have gone down, and therefore the average to percentage is bigger. And suddenly at 90 we don't have peaks or plateaus. Oh, we don't have peaks because there's no innovation. 100% same. Let's have a look at when it's 100 items that we're talking about. Maximum error is 77 out of 88. Average to percentage plot, usual, heads. When do we hit 77? At 75% we do, and then we suddenly don't. So at 75%, let's go look at that. This is when we have it. Then again, the average plateau level is steadily decreasing. It was once at 64, and it went all the way down to 53, 53, 52, 52, 52, 52, 52. So the point still stands. There's little to no dips, or the dip size percentage is small when you have a lot of items. The average dip size percentage, or the dip size percentage, or the dip percentage in terms of size, is small because the entities don't peak anymore, which is due to the fact that there is little innovation through procreation, and any kind of improvement can only be made by mutation, and which is quite unlikely. And to do that, because there are 100 items or 100 genes, to get the right kind of mutation, or to get the right kind of series of mutations. Well, if any entity was to improve, it would have to make certain changes, but only through mutation. And since mutation rate is at 3%, and we're dealing with 100 items, it's very unlikely that this will happen. Yeah, I think that's one of the reasons why when we only have 10 items, this happens, but when we have 100 items, that doesn't happen. So that's all 7 notebooks. I do need, but yeah. Next, I think I'll try working on switching the distributions per set of values. That's 42 combinations, 42 permutations rather, and see where it goes. I mean, but that's going to be 42 notebooks, or not? I don't know. And after that, I also need to change some of the evolution logic, so that even when the entities are not being struck out, I start introducing new entities into the population, through procreation, by maybe allotting certain number of, by allowing a certain number of new entities to be created through procreation. Like for instance here, one single stroke could do that. Yep, I'll see how that goes. Okay. Yeah. By doing these series of, by making these series of notebooks, I have unintentionally proved to myself that maximum constraint percentage is, well, high maximum constraint percentage values actually don't allow for innovation, but only because I made it that way by not introducing, or by not allowing for procreation there. Yeah. So still a lot of work to be done. Hours and hours of notebook, hours and hours of Jupyter Lab. Okay, that's good. Well, that took 71 minutes. Wow. Almost as long as it would take me to run this 100 items part. Or longer than that. Anyway. Okay, thanks for watching. Bye.